Welcome to the Basics of Spectroscopy video series. Let's talk about potential energy. Potential energy is the potential or stored energy of an object due to its position. We are all already familiar with this concept. Two masses that are separated by some distance have an associated gravitational potential energy, while two charges that are separated by some distance have an associated electrostatic potential energy. We'll have learned about this in high school and first-year university physics, and we'll have already seen the analytical expressions for these two potentials. If we're thinking about the electrostatic potential for an electron and a proton, and represent this graphically, we see that it actually has the same form as the gravitational potential. Both potentials are attractive. In other words, the potential energy decreases as R decreases. Note that the charge of the electron in the electrostatic potential is represented by the lowercase q. In this case, it's negative. If both particles had the same charge, the electrostatic potential would be repulsive. In other words, the potential energy would increase as R decreased. Understanding electrostatic potentials is important for understanding atomic and molecular systems, since matter is composed of charged particles. Our example of the electron-proton system is, of course, the hydrogen atom. Well, what about molecular systems, you might ask? It turns out that the electronic energy depends parametrically on the internuclear distance, at least within the Born-Oppenheimer approximation. This means that we can generate an electronic potential energy surface by calculating the potential energy at all possible geometries of the nuclei. This usually isn't an easy task. Instead, it's sometimes useful to adopt a simple approximate model, like the ball and spring model. This is also known as the harmonic oscillator. If we stretch a spring, the potential energy increases. Likewise, the potential energy increases if we compress the spring. When the forces acting on the nuclei are zero, this corresponds to a stationary point on the potential energy surface. This, of course, will be at the bottom of our parabola. For molecular systems, this corresponds with the equilibrium geometry. But the harmonic oscillator is not really that great a model for molecules. When atoms are very close, they repel very strongly, so the repulsive part of the harmonic oscillator potential isn't quite steep enough. More importantly, as chemists, we know that as chemical bonds stretch, they also can break. This means that molecular potentials must be anharmonic. As atoms move apart, the potential energy must asymptotically approach the bond dissociation threshold. We can model this and the short-range repulsive behavior using a Morse potential. Here, K is the bond force constant, and dE is the bond dissociation energy. It turns out that the Morse potential is actually oftentimes a good model for molecular potential energy curves. Consequently, when discussing molecular electronic states, people will often draw Morse potential energy curves. You'll see more of this in the electronic and vibrational spectroscopy masterclass videos. I hope that you found this short video on potential energy useful. See you next time.